Last episode, we left an engineer staring at a dashboard that had run out of room. Tonight, let's watch what happens next. It's 8 in the evening. The big billion day sale just went live, and a few million people tapped buy in the same breath. All of them, all at once, land on the same app. And right now, that app is running on one server. Watch what happens to that one poor machine. So, how do you serve millions of people at once when one server clearly can't? That's the whole episode. Before we fix it, let's be honest about why one server melts. Because it's the reason everything else exists. A server is just a computer. It has a fixed amount of CPU and memory, same as your laptop. Every request it handles eats a little of both. A trickle of traffic is fine, the machine barely notices. But pour a big billion day crowd onto it, and the CPU pins at 100%. Requests start queuing. And the P99, the unlucky user number from last episode, goes from milliseconds to nearly 4 whole seconds. The machine isn't broken, it's just full. And a full machine has only 2 ways out. The first idea is the obvious one, and honestly it's the one most people reach for. If the machine is full, get a bigger machine. This is called scaling up or vertical scaling. Same single server, just beefier, more cores, more memory, faster disks, and it genuinely works. The bigger box swallows the same crowd and the load bar drops back to comfortable. No new architecture, nothing to rewire, you just upgrade the hardware and go home. So if it's that easy, why doesn't everyone just keep buying bigger machines forever? Because scaling up runs into 3 walls, and they're brutal. Wall number 1. There's a biggest machine. You physically cannot keep doubling the cores in one box. At some point, you've bought the largest server that exists and the traffic is still climbing past it. You've hit a hard ceiling. Wall number 2. The price. Going from a small server to a medium one is cheap. Going from huge to enormous costs wildly more for each extra bit of power. The cost curve doesn't rise, it explodes. And wall number 3 is the scary one. It's still one machine. One power supply, one thing to fail. When that single beautiful server falls over at 2 in the morning, your entire app is gone. All of it, instantly. Bigger just means a bigger single point of failure. So here's the shift that changed how the whole internet is built. Instead of one giant machine, you run many ordinary ones. This is scaling out or horizontal scaling. Not one hero server doing everything, but a fleet of plain, boring, identical machines sharing the work between them. And the magic is when the crowd grows, you don't rush out to buy a bigger box, you just add another cheap one to the fleet. Traffic doubles on sale day, you double the machines. Traffic drops back at midnight, you switch some off. Best of all, if one machine dies now, the others just carry its share and the app stays up. No single point of failure. This is how you serve millions, but it hands you a brand new problem. You've got 6 identical servers now, all ready to work. A request shows up. Which one handles it? You can't exactly put up a sign telling users, please connect to server number 4 tonight. They don't know your servers exist and they shouldn't have to. Somebody has to stand in the middle, take every incoming request and decide, you go here, you go there. So the work spreads evenly and no single machine gets buried. That somebody has a name. Picture a restaurant on a Saturday night. Not one kitchen, several identical kitchens, all cooking the same menu. Now the diners crowding at the door have no idea which kitchen is free. So the restaurant puts one person at that door, a waiter, whose only job is to look at the kitchens, see who's least busy and send each new diner to a free one. The diners never think about kitchens, they just walk in and food arrives. That waiter is doing something invisible but essential, spreading the crowd so no single kitchen drowns while another sits idle. In a real system, that waiter is a load balancer. Every request from every user hits the load balancer first and it forwards each one to whichever server in the fleet is best placed to handle it. One front door, many kitchens behind it. That single idea is what turns a pile of servers into a system that scales. But wait, how does the waiter actually decide? When a diner walks in, which kitchen do they pick? Because just send it somewhere isn't a plan. The load balancer follows a rule for choosing, and that rule is called a load balancing algorithm. There are a handful of these, each with a different personality. Let's meet the three you'll actually run into. The simplest rule is called round robin, and it's exactly what it sounds like. Take turns. First request goes to server 1. Next request, server 2. Next, server 3. Then back to 1, and around we go. Nice and easy, and for a fleet of identical servers all doing similar work, it's often plenty. But round robin has a blind spot. It doesn't look at how busy each server actually is. If server 2 got stuck with one monster request that takes 10 seconds, round robin doesn't care. It'll happily send it more work anyway because it's just counting turns. Which leads straight to a smarter rule. The smarter rule is called least connections, and it fixes exactly that blind spot. Instead of blindly taking turns, the load balancer looks at how many requests each server is handling right now and sends the next one to whoever's carrying the least. The busy servers get a breather while the idle one picks up the slack. So the load actually evens out instead of just looking even on paper. This matters a lot when requests aren't all the same size. There's a cousin of this called weighted balancing for when your servers aren't identical. Give the bigger, faster machine a higher weight and it's handed a larger share of the traffic on purpose because it can take it. The third rule solves a different problem. What if a user needs to keep landing on the same server? Say a user's shopping cart is being held in memory on server 2. If their next request bounces to server 5, the cart's gone. Server 5 has never heard of them. So the load balancer can take something stable about the user, like their IP address, run it through a hash, a quick bit of math that always gives the same answer for the same input, and use that to always send them to the same server. Same user, same kitchen every time. This is called sticky sessions, and it's handy, but it's also a warning sign we'll come back to. Pinning a user to one machine quietly makes that machine special. And special machines are exactly what horizontal scaling was trying to avoid. Now, not all load balancers are equal. There are two flavors, and the difference is how deeply they read your traffic. A layer 4 load balancer works down at the transport level. It looks at just the basics, the source, the destination, the port, and forwards the packets on without ever opening them up. Because it never reads the actual content, it's blazing fast and dirt cheap. It doesn't know if you asked for a photo or a payment, and it doesn't need to. A layer 7 load balancer works up at the application level, where the real request lives. It can actually open the envelope and read it, so it can send everything under checkout to your payment servers, and everything under images to a fleet tuned for photos. That intelligence costs a little speed and a little money, but it unlocks routing that layer 4 simply can't do. Fast and dumb or slower and smart, that's the choice. So, where does this waiter actually come from? You've basically got three options, from old school to cloud. 1. A dedicated hardware appliance. A physical box that sits in the data center and does nothing but balance traffic. Fast and rock solid but expensive and something you have to buy and rack yourself. 2. Software like Nginx or Hair Proxy. It's just a program running on an ordinary server, which makes it cheap, flexible, and what most teams actually use today. 3. A managed cloud load balancer like the ones AWS or Google rent you. You don't install anything or babysit it, the cloud runs it for you, and it scales itself. And there's of course a cousin that works even earlier. At the DNS level, the address book step from episode 2. used to spread users across entire regions before they ever reach a single data center. Same idea, different altitude. Here's something that surprises people. Once you've put a waiter at the front door, it's the perfect place to hand off a few other chores too. The biggest one is encryption. Every secure connection, every little padlock in your browser has to be decrypted before the server can read it. And that decryption is real work. So, the load balancer does it once at the door. It terminates the secure connection, decrypts the traffic, and passes plain, already open requests to the fleet behind it. This is called TLS termination, and it means your servers don't each waste effort on the same encryption maths. While it's there, it can also compress responses and swat away obviously bad traffic. The front door turns out to be a great place to get a lot of shared work done. Now back to that waiter, because the smartest thing it does is also the quietest. It never stops checking whether the kitchens are alive. Every few seconds, the load balancer pokes each server a little health check, asking basically, "You still there?" Healthy servers answer and keep getting traffic. Then one server chokes, maybe it crashed, maybe it froze. It stops answering the health check. The moment it misses a few checks, the load balancer quietly pulls that server out of rotation and stops sending it anyone. Users feel nothing. Their requests just flow to the healthy machines instead. This is the real reason a fleet survives a node dying at 2 a.m. where the single big server couldn't. So load balancers are the hero of this episode, but a good engineer always asks, what does this cost me? And there are 3 real risks. Risk 1, you just made the waiter a single point of failure. Every request now goes through the load balancer, so if it falls over, it takes the whole app down with it, the exact problem we were running from. Risk 2 is that sticky sessions warning from earlier. If a user's session lives only on server 2 and server 2 dies, they're suddenly logged out with an empty cart because the data was trapped on one machine. The fix is to keep your server stateless, hold the session in a shared place, so any server can serve any user. We'll build exactly that in the caching episode. And risk 3, a badly chosen algorithm can still pile a stampede onto one poor server. So balancing isn't automatic, it's a decision you have to get right. Which leaves the obvious question, if everything now runs through the load balancer and the load balancer can fail, who's watching it? You don't get to just ignore that. The answer is you never run just one, you run at least 2. The simplest setup is active-passive. One load balancer does all the work while a second sits quietly beside it, watching. The instant the active one dies, the standby takes over its address in seconds, and traffic never notices. A backup waiter ready at the door. Bump it up to active, and both load balancers work at once, sharing the load and covering for each other. And to spread traffic across them, you go back to those earlier tricks, DNS handing users to different load balancers, or a clever routing scheme called Anycast that sends you to the nearest one automatically. Redundancy all the way down. That's the real shape of a system that stays up. So let's zoom all the way back out. When one machine can't cope, you have 2 moves. Scale up, buy a bigger box. Simple, but it hits a ceiling and stays a single point of failure. Or scale out, run a fleet of ordinary boxes, which scales almost without limit, but only works if something spreads the traffic across them. The something is the load balancer, the waiter at the door, picking a free kitchen for every request, checking they're all still alive, and never letting one machine get buried. And the deeper trade-off underneath it all, the moment you go horizontal, your servers have to become stateless, interchangeable, forgettable. Hold nothing precious on any single one. But look, we now have a whole fleet of servers that all need to talk to each other and to the outside world. How do they actually do that without descending into chaos? There's a contract for it and it's called an API. That's next episode.